Throughout the 1980s, rallying has been dominated by four-wheel drive cars. The first was the Audi Quattro. However, despite its unparalleled success as a rally car, the Audi Quattro was in fact developed primarily for road use. Since then, Audi Volkswagen have introduced a range of four-wheel drive cars which are designed purely for on-road use. They're not intended for off-road driving. For one reason, they have limited ground clearance. Although there are exceptions, the Volkswagen Type 2 Synchro models have been specially adapted to cope with off-road conditions. But what advantages does a four-wheel drive car have for everyday use? Let's begin by looking at the principles of four-wheel drive. Many manufacturers have developed their own systems, but all share the same basic layout. The power from the engine can be transferred to the front and rear wheels at the same time. A means of allowing one wheel to rotate at a different speed to the other on the same axle is the differential. So a differential is required on the front and rear axles. It's also necessary to allow for a difference in speed between the front and rear axles, for example on braking, cornering, or acceleration. This can be achieved by a differential unit between the front and rear axles. Therefore, a front, center, and rear differential are required for a permanent four-wheel drive system as used by Audi. Other manufacturers' part-time selectable four-wheel drive systems do not employ a center differential. Basically, the two-wheel drive car becomes four-wheel drive once the two axles are joined by operating a locking device between the two differentials. This results in constant engaging and disengaging of the system to maintain control in varying road conditions. Unlike our permanent four-wheel drive system, its only benefit is for off-road or winter usage. But why is it an advantage to have all four wheels permanently powered? In the days of Roman roads, corners were a distinct rarity. Today, however, once we leave the intercity and urban motorways, corners and bends are frequent. With permanent four-wheel drive, the tyre traction capabilities are increased by 50% over a conventional two-wheel drive system when comparing both vehicles travelling at the same speed with the same tyres. The compound and condition of the tyre plays a major part in road holding, whether it's a two- or four-wheel driven vehicle. Let us assume that the road surface is good, dry, and we are using new tyres. The tyre has an area that can be calculated within which it will retain safe adhesion with the road surface. This calculation is based on the coefficient of friction between the road surface and the tyre. A circle can be drawn to show the area within which the tyre forces must not exceed to maintain traction. On a two-wheel drive car, the driving force is transmitted equally to both front or rear wheels only. The force exerted by cornering acts at 90 degrees to the tyre. The resultant force can be calculated by multiplying these two forces together and inserting the force vector. This line of force exceeds the maximum area of traction. The tyre will not continue to grip unless the forward force is reduced by deceleration. A four-wheel drive car, travelling at the same speed, divides this power between four wheels, so the forward force at each front or rear wheel is halved. Carrying out the same calculation as before, it can be seen that there's a reserve of power available before losing traction. We've mentioned that 100% of the engine power is transferred to one axle on a two-wheel drive car. Each road wheel will receive 50% of that power. If the road surface is affected, for example by wet or icy weather conditions or contaminated by diesel spillage, then this circle of traction will be reduced. Each axle on a four-wheel drive car receives 50% of the engine power and therefore 25% to each wheel. This reserve of power can ensure stability should the road conditions change. Cornering stability characteristics are also dependent upon where the power is put onto the road. On a front-wheel drive car, the rear wheels are pulled behind and do not apply any forward forces. The total forces on the rear wheels act towards the curved center point. The car understeers. The reverse occurs on a rear-wheel drive car. The front wheels have no forward forces applied, and so all forces on these tyres act toward the curve's centre. The car oversteers. On a four-wheel drive car, the power is distributed to all four road wheels, dependent upon the traction speed of each tyre. Stability is maintained. Another area that is critical to road holding and handling performance is the correct alignment of all four road wheels, which can be adjusted at the rear as well as the front. The video series Tyre Wear and Suspension, Tyre Behaviour and Vehicle Handling, and Vehicle Alignment, numbers 11, 16 and 20 respectively, cover the many reasons and setting up procedures to optimise traction and reduction of tyre wear. Section 6 of Vehicle Alignment shows the use of the Unilux alignment equipment for checking and adjusting the rear geometry on four-wheel drive cars. The advantages of four-wheel drive can be lost if the rear tracking is not correct. The rear wheels being driven will lead to poor cornering and straight-line handling, causing tyre wear. The original Audi Quattro divides the engine power equally to both the front and rear axles 50-50 permanently. The ratios of the front and the rear differentials are the same. Power from the engine is transferred to both differentials via the gear train, central differential and prop shaft. All four wheels are driven when a gear is engaged. During cornering, the inner wheels, those on the side of the curve, are able to rotate at different speeds to the outer wheels by the action of the front and rear differential units. The front wheels are allowed to rotate at different speeds to the rear wheels by means of the center differential unit. This first method of transmitting the power to all four wheels incorporated a mechanism which allowed the center and rear differentials to be locked. It's only necessary to select the central differential lock whilst driving slowly in adverse road conditions, such as roads affected by loose gravel, snow, ice, or diesel spillage. Speeds up to 20 miles per hour would be considered normal in these conditions. The rear differential must only be engaged when the car is immovable in mud or snow, for example. In this condition, power can be directed to both rear wheels equally to get out of a difficult situation. Once the car is moving on firmer ground, the rear lock must be disengaged. Incorrect use of the central or rear and central differential locks will result in wind-up of the axles, prop shaft and gear train. Let us see the effect of locking the center differential on a dry, well-surfaced road. In the straight-ahead position, all wheels turn at the same speed, provided that all tyres have exactly the same degree of wear. On cornering, however, all four wheels rotate at different speeds to each other. Remember, the power from the engine is divided equally via the front and rear differentials. With the center differential locked, a rigid drive between the front and rear axles is unable to compensate any speed difference between the two axles. Tyre wear, caused by scrubbing, as well as poor handling at speed, will result. The powertrain will twist to absorb power from the engine that cannot be transmitted to the road wheels. In severe cases, something is liable to fail. This situation is made worse if the rear differential is also locked. The rear wheels are turning at different speeds through a solid axle, and the front and rear differentials are solidly connected also. Not only is the handling severely affected, but excessive strain on the whole drivetrain can be disastrous. Tyre life will be greatly reduced. So, a full understanding of the use and effects of differential locks is essential when using this arrangement. All Audi cars are now available with four-wheel drive. Continuous development has improved the capabilities of the original system further. A torque-sensing, torsion, central differential has been introduced to replace the original selectable unit, thus enabling even better permanent four-wheel drive performance. The chances of selecting the central differential lock incorrectly have been ruled out with this type of variable power transfer differential. We'll be taking a closer look at this system later. The Volkswagen Synchro models offer a different four-wheel drive system to that of the Audi range. Type 2 Transporter and Caravelle models are now joined by a Golf Synchro. These models have a two-wheel drive arrangement that will automatically transfer the power to the other two wheels when slip occurs to the driven wheels. The four-wheel drive system is always in action. Distribution of power from around 0 to almost 100% from the normal driven axle to the other axle is achieved via a viscous coupling. The viscous coupling engages the power quietly and progressively between the axles and dampens out oscillations within the drivetrain. We mentioned earlier that the four-wheel drive Type 2 models were the only vehicles manufactured to cope with cross-country or off-road conditions. Many off-road characteristics have been incorporated into the design. Increased ground clearance, under-frame protection plates, bars and strengthened suspension are standard on all models. Front and rear differential locks are standard. In its basic form, the viscous coupling arrangement copes with all road conditions. The differential locks are purely for applications that involve severe off-road usage. The standard road tyres are not recommended under these conditions. The Golf Synchro uses the viscous coupling together with a rear differential lock arrangement as standard. This can be likened to the Audi Quattro version using the Torsen differential layout. Having seen the benefits and development of four-wheel drive systems on both Audi and Volkswagen, let us now continue with a deeper investigation of the various four-wheel drive layouts. All Audi Quattro versions, up until the introduction of the 1987 model year Audi 80, employ a modified 016 5-speed transmission unit. The pinion shaft is now two separate components. The pinion shaft itself runs within a hollow output gear train. This is how it works. The inner shaft is connected to the center differential gears, while the outer, hollow gear train is connected to the center differential outer housing. Power is transferred to the front axle along the pinion shaft. An output shaft is splined into the other side of the differential gears, which is connected to the rear axle by means of a prop shaft. Power is transmitted equally to both the pinion and the output shaft. In normal operation, power is distributed to the front and rear differentials via these gears. A manually operated locking mechanism is fitted between the output shaft and the differential housing. Once this lock is engaged, there's no speed difference possible between the front and rear axles, and therefore the unit rotates as a solid coupling. The lock was originally engaged by means of a cable. This is now carried out pneumatically by vacuum servo units. The later version has a rotating switch that can select the central differential or both differentials. Warning lights operate for driver information. The ABS system is automatically disengaged when a lock is operated. Its main disadvantage is that the driver needs to understand when to use and when not to use one or both differential locks. To obtain maximum benefit from this system, the center lock would need to be engaged and disengaged when driving in changing road conditions. This is not always practical with a manual system. The Audi 80 Quattro, from model year 1987, uses a torque sensing unit in place of the center differential, which automatically varies the power between front and rear axles. During driving on slippery road conditions, the power is constantly directed to the road wheels with the maximum traction. This also applies when cornering. When driving on gradients or accelerating and decelerating, power is once again directed to the axle with a greater driving force. A new O1A gearbox replaces the previous unit. The principle for power flow remains the same. The torsion unit transmits the power to whichever output shaft is revolving more slowly than the other. This is achieved by transmitting the power through a worm gear arrangement to the output shafts. Under normal driving conditions, the power transmitted to each output shaft is the same, that is 50-50. Should a wheel spin on one axle as a result of loss of traction, the torsion unit will transfer power to the opposite axle, up to a ratio of around 3.5 to 1. The torsion differential can account for differences in wheel speeds under braking, making it fully compatible with ABS. Remember that the rear differential is only an aid for driving off in bogged-down conditions. If selected manually, it's automatically unlocked above speeds of 15 miles per hour via an electronic control unit situated under the rear seat. The Volkswagen Transporter, Caravelle and Golf Synchro models achieve power transfer to all four wheels via a viscous coupling. Let us look at the Transporter and Caravelle versions first. As before, a prop shaft connects the front and rear differentials. In place of the center differential, a viscous coupling is fitted. The front wheels are driven when one or both of the rear wheels rotate faster than the front wheels. The viscous coupling contains a series of plates totally sealed in a silicone fluid. Each of the 30 alternate inner plates are connected to the input side by the prop shaft. The remaining 29 plates are connected to the output side shaft to the front differential. Should the rear wheels rotate faster than the front wheels, friction takes place between the alternate inner and outer plates and the silicone fluid between them. This results in a rise in temperature of the silicone fluid. The viscosity of the fluid increases and transfers the driving force from the input side plates to the slower output side plates. Power is transmitted smoothly to the front wheels. Originally, the drive to the front wheels would occur when a difference between the rear and front wheel speeds was approximately 6%. This difference has been modified to around 10% to reduce wind-up in the drivetrain when turning tightly, for example when parking. The Golf Synchro takes the development a stage further. On differing road surfaces, the power will be automatically transferred from the driving axle to the other axle to maintain maximum drive and traction. This is the case for the Type 2 and Golf range. Taking the already tried and tested front-wheel drive system, a drivetrain has been added to couple the new 009 5-speed gearbox to a rear axle differential via a viscous coupling. On dry roads, the viscous coupling transmits only a small amount of power to the rear axle. It automatically transfers an increasing proportion of drive if slip at the front axle increases. Almost 100% of the power can be transmitted to the rear if necessary, depending on the surface conditions. When braking, speed differences also need to be accounted for. Power needs to be distributed in such a way as to prevent the rear wheels locking to maintain directional stability. Four-wheel drive systems with a fixed linkage cannot guarantee this. All four wheels can lock. Directional stability is lost. The Golf Synchro has a unit in the rear differential assembly which allows the rear wheels to freewheel. For example, when braking, the rear wheels do not lock prematurely, and directional stability is maintained. The system is fully compatible with ABS. This freewheel device is automatically activated on overrun. The freewheel lock operating unit is activated by means of an electronic control box and intake manifold pressure. The self-study program, number 78, Golf Synchro, describes its operation in detail. The modern generation of Audi Volkswagen four-wheel drive systems allow the power from the engine to be distributed efficiently between the four road wheels and transfers the torque automatically to the front or rear axle depending on the traction available. Areas to consider when fault finding. The main areas of customer complaints are generally related to handling, unusual tire wear characteristics, poor disengagement of differential lock or vibrations. This program has been written to enable the service team to understand all current four-wheel drive concepts and advantages. The first two items, handling and tyre wear, can be purely a case of driver error. On early Quattro systems, incorrect use of the central or rear and central differentials will cause tyres to scrub and affect handling. Incorrect front or rear steering and suspension alignment will also result in tyre wear and handling problems. Remember, the settings are critical on a four-wheel drive vehicle. Uneven tyre wear on any axle can result in wind-up of the axle or drivetrain. Effectively, the worn tyre rotates at a different speed to the other road wheels. The differential lock will not disengage when wind-up is present. It may only disengage when the vehicle is reversed or when at least one road wheel is raised, thus releasing the strained drivetrain. If this is the case, check for uneven tyre wear and ensure that the customer is aware of the use of differential locks. It's therefore essential to consider this program, together with tapes number 11, 16 and 20. The program Vehicle Alignment includes the procedure for rear wheel checking and setting. The Volkswagen Synchros, with viscous coupling, develop a characteristic when tight reversing maneuvers are carried out. The viscous coupling action is reversed and acts as a solid transfer arrangement. Wind-up will occur only in this situation. This is not a fault with the system, but an area that must be recognized when dealing with owner complaints. Vibrations can often be as a result of unusual tyre wear. However, the alignment of the prop shaft or gear train must not be overlooked. This tool, 3139, must be used when removing and aligning the prop shaft. Full details of removing, installing and aligning the prop shaft will be found in the relevant workshop manual. All information for transmission or drivetrain alignment must be observed when carrying out repairs or adjustments to vehicles fitted with four-wheel drive systems. Four-wheel drive is here to stay. We hope this video and the accompanying workbook will help you understand its principles and advantages.